Hello class and welcome back to Sketch Science. Today we're talking about fields. What is a field, you might ask? What is it? Is that where like farmers grow things, right? That's like this ground over here with the corn stalk sticking out of it. That's a field, right? It's got things No, we're not talking about that as a field today. Yes, that is a type of field. Well, maybe what about a profession? Nope, that's not the type of field we're talking about either. What about a field of study? Nope, not that either. Today we're talking about fields when it comes to like gravity, electricity, magnets. It's the area which force can be observed from a distance. Now, I say observed, not seen, because fields are actually often invisible. Well, pretty much all the time they're invisible. You can't see a magnet pulling on another magnet. Like, you can't see it physically pulling. Yes, you can see a magnet or a piece of metal drawn to another magnet. You can sometimes see a spark between two objects that are electrically charged. You can see an apple fall out of a tree to the ground. But you can't see electricity floating in the air. You can't see magnetic pull with your bare eyes. You can't see gravity. Because if you think about it, gravity is an invisible force caused by the mass of an object. What does that mean for seeing? Well, you can't see it. That's why we call it a field. A field is that area which that force has like ability, where it can move something. So there are really three that we're going into today. The first would be magnetic. Now, magnetic fields, think about it. A magnetic field is kind of the area in which this magnet over here can attract other metal. Remember the whole ferrous metal thing we went over before when we talked about magnets? The area which this magnet can attract any piece of ferrous metal. So I'm just doing Fe because that's iron. That's the periodic table thing for iron. So a field is the area which this magnet will have an effect on that iron. Remember, there's north, south pole and all that. If you looked at a bar magnet, so if we were to look at a bar magnet, its field would look something like this. Now, one side would be north, one would be south. For this, we'll call the red north and this south. Oh, it's going to stay underneath the red. That's okay. So, north is red, south is white. If we were to say on here, we would have arrows pointing to one of these. So, it always flows from one to the other. We'll say it flows from north to south. Yes, the field would take like those curved lines from one to the other, because remember, opposite poles attract each other. So things that are attracted to a north pole would pull into the north, things attracted to the south would pull into the south. But they also attract each other. So their fields go around from north to south, because it's going to pull things to the north side, it's going to pull things to the south side, but the poles also pull on each other. So what it would really look like is you'd have arrows coming out here. So if it was flowing from north to south, you have arrows there. That's what they kind of look like, because fields are shown by arrows, these things called field lines. Field lines. They're always these arrows, and depending on how close they are together. So what it would really look like is there'd be a ton of arrows over here, and a ton of arrows coming in here, because that shows that there's more force in those areas. And as you get further out, the arrows become farther and farther away from each other. That's how they show like how strong something is. So in a bar magnet, it would go from north to south. You'd have a lot more arrows closer to the magnet than farther away. And it would show kind of this flow. You could use like the full lines that we had before, these whole circular or elliptical lines following these paths. But to show you the strength, you would have more closer on. So why they do this is, and how they observe this is, they took these little metal shavings, these little things, and they sprinkled them all over a magnet. So if I were to erase all of this again, they sprinkled it all over these magnets in all the parts of it. And what they saw was there was a lot of sprinkles that would fall on the ends of it. On the ends of the magnet, they'd all stick over on. And then there would be some that would kind of trickle around. So if they sprinkled these little pieces of dust around, this was kind of the shape they went in. So they'd all stick to the ends, and then they'd go around a little bit on the outside in these little band shapes. That is how we could see a magnetic field without actually being able to see it. Now the next type of field, that's magnetic. It goes from north to south or south to north. The arrows go from one to the other. Arrows are field lines. That's the word for it. They're the same in electric too. So if you had two positive charges, remember how in electric and magnetic both are opposites attract? So in this case, when you talk about electric, arrows, the field lines point away from positive and towards negative. So if you had a positive, the arrows would point away. They'd point up this way, out that way, out that way. But the reason I want to put two positive next to each other is because, yes, you could say they both have the push that way. But if you think about it, they'd actually push up this way. So this little centerpiece, because they push away from each other, think about it, their fields will push away from each other. So it's like they run into each other. And yeah, then they have their normal push out here, normal push out here. These ones are all straight, but when you get them next to each other, they curve because they don't want to touch each other. Their fields don't even want to touch each other. They push away. Now, if you were to change this and turn it into a positive and a negative, it would look like this. All of the positives on the other end, it'll be fine, but all of the positives are going to try to go around to the negative. and all of the negative are going to come from around the positive. So while positive pushed away, negative and positive, they suck towards. It goes down towards. The positive wants to be pulled to the negative. And finally, if you changed it and you made it two negatives, well, once again, they get pulled in towards each other, but they also push each other away. So the individual charges push each other away, but as they pull towards each other, it's going to curve kind of like the positive did. So if you think about it, positive, negative, one pushes, one pulls. But if two are pulling, they're all pulling around. Because if you think about it, if you drop an object right in the middle, you drop an object right here, it won't get pulled towards either. Like if you put a positive in here, it'll be even pulled to both sides. But as soon as you move it a little bit this way, it'll get pulled into here. If you pull it a little bit this way, it'll get pulled into here. That's why it shows these arrows. These field lines show you the path an object will take if it's attracted to that object. So this, if you put an object on this line, it would follow it to the negative charge. If you put it on this line, it would follow it to this one. So we've gone over magnetic, electric. What about gravity, gravitational? So we know magnetic gets it through its poles, through its domains. So magnetic is caused by poles, domains in a ferrous material. Electric is caused by charges. Everything has electric charges in it. That's protons, electrons. Those are in your atoms. The atoms of every piece of matter in the universe, they all have them. So anything could be electrically charged. The last one's gravity. Everything with mass has gravity. Gravity is caused by mass, not weight. Weight is a byproduct. Weight is caused by gravity. So a certain amount of mass in a certain gravitational pull will have a certain amount of weight. We're not getting into that today. But gravitational, it's caused by mass. But it uses the same field lines. Remember, field lines are like those arrows. And depending on how many there are, how close together they are, that's how it shows how strong something is. But if you had the Earth has gravity. The moon, I'll do E for Earth, M for moon, also has gravity. How you would draw how this gravity interacts, yes, the Earth has a lot of gravity pulling directly in. Gravity, though, always pulls to the center of mass. So the Earth's gravity would pull to this red dot right here. Everything would get pulled to the red dot. The moon, everything gets pulled to the red dot in the center. So all of these arrows, if you look where they point, if you drew a line from where they point, would always point towards the center. Now the moon, yes, it would get some here. The Earth's gravity, keep in mind, will pull a lot further because look how much more stuff, look how much bigger. Remember, mass is how much stuff's in something. The Earth has a lot more stuff than the moon does. So it will pull from further out. So these arrows will go from a lot further out than the moon's will. Because of this, we'll have arrow here, arrow here, arrow here, arrow here. Because of this, as it gets closer to the moon, yes, the moon will have its own arrows out here. But as it goes around the moon, it'll actually look like this. Because once you get to a certain point, it will actually pull towards the Earth instead of towards the moon. So there's still that little bit that'll pull to the moon here because you're still close enough. But because of the Earth's gravity, once you get in here, it's kind of you're between them. Once you get towards the Earth's gravity, it will actually pull an object. And that's the point of these field lines, is to show that if you had something here and it was traveling this way, if you have a rock up here, it's traveling this way, it gets this little crossroads here. If it keeps moving in this direction, it will actually follow all the way down to Earth. So I'll use blue for that. If it's traveling down this way, down this field line, if you follow the field line, it will make its way to Earth. But if somehow it travels this way, if this object starts traveling this way, it will actually go and run into this field line and go to the moon. That's the split between their gravitational pulls, their fields. The moon's field kind of stays in this area. The Earth's is this entire page, but since the moon has more control than the Earth in this one circle, so this one circle here has more control given to the moon due to its field than the Earth. Anything outside of that circle, though, and an object will actually, even though it's a lot closer to the moon than to the Earth, will go down to the Earth because of the gravitational field. It's stronger because the Earth has more gravity. Field size and strength is determined in gravity by mass. So the more mass it has, the stronger it will be. Electricity, how strong your charge is. If you have 5 positive charges, 2 negative, then your strength will be 3 positive. It's just simple addition and subtraction for strength. Magnetic depends on the material and the size of the magnet. So that's what a field is. Remember, fields are invisible areas around an object where force can be observed. Fields are invisible areas around an object where force can be observed. Fields differ depending on the object's, the strength of its force, size of the object, different things like that can affect your field size. But fields are that invisible area around an object where a force can be observed. It's the area around a magnet that will still attract metal. It's the area around a charged object where you can have a spark or a force come off, an electric force. It's the area around a planet, around even a person, where their gravity takes effect. And they're shown in maps. You can map them using field lines. Field lines are arrows that show or map the flow of force in a field. Depending on how dark depending on the brightness or darkness of the arrow, depending on the size of the arrow, how many arrows, how close together they are, that's what shows how strong something is. So field lines are those arrows that show it. Fields themselves are the invisible area where the force can be observed. If you have any questions or comments on how to make the video better, please leave them down below. Be sure to like the video if you liked it, or so you can find it easier, and subscribe so you don't miss any more videos and you can find the channel easier when you want to learn more. Thank you again for watching, and have a great day.